那就可以了。啊，麦克风在这里啊。Hello。So, so should we start? 还是等一下？
Okay. Let me yeah. Let me probably introduce you.
Okay.
Only one mic.
There's another one.
Oh, there's another. Okay. I think before Professor Z start, I should say a few words. Okay. Professor Yu Fang is still abroad, as I understand, and I'm Guang Yuguo, Director of Physics Division. Okay, and I'm very, very happy to see Professor Z again. He used to come back, well, not back, to Physics Department to give lectures and the summer school for many, many times. Okay, so it's at least I'm very happy to see he's coming back again to give 3 lectures this week, is it? Okay, so as all of you know him already, he's a renowned professor in Santa Barbara's, and now today he's going, this is the first of 3 lectures he's going to give. The title is Fly by Night Physics, and this is the first one. Let's welcome Professor Z.
I'm very, let's see, is this working? I'm very happy and honored to come back to the National University of Taiwan. As was mentioned, I have spent, I used to come to Taipei every year, but this time because of the pandemic, I haven't been back for 4 years. So it's particularly a pleasure and exciting for me. And is this working? Yes. So Taida has, of all the physics institutes and universities in the world, and I have visited, I don't know, hundreds, maybe close to 1,000. And I was just in Argentina and Chile. Of all these universities in the world, National University of Taiwan, Taida, has special meaning for me because that's where I met my wife on campus in front of the gym. 台大体育馆 has 对我来说是一个非常特别的地方。Okay, so today I want to talk about my book, Fly-by-Night Physics. I'll give 3 lectures altogether, 2 this week and 1 next week. And then after that, I'll go to Beijing to give the same lecture. So this has been published as a book, Fly-by-Night Physics by Princeton University Press. Let me see if I can control this. So, how do you get rid of all this other stuff? The orange and black. So it's based on a course I actually invented at the University of California in Santa Barbara. And just recently, just a few months ago, the chair So we have, in the physics department, we have these special topics courses. So the undergraduate core curriculum, of course, consists of classical mechanics, electromagnetism, quantum mechanics, and statistical mechanics. So those are the four required courses, and then we have all kinds of extra courses. They're called special topics course. But just recently, a few months ago, the chair of the physics department, who is a particle high energy experimentalist, Claudio Cabanari, he has proposed to make it a regular part of the curriculum. So it'll be a regular course instead of a special topics course. There's no difference to me whether it's special topics or regular course. The only difference is that because if it's a special topics course, then students and so on have to ask the undergraduate representative for permission to take the course, et cetera, et cetera. Okay, so my motivation for writing this book, it was set forth in the preface. Many years ago, decades ago, I arrived at Princeton University to study physics, and only having a very vague idea what physics is about. So John Wheeler, because this is a long story anyway, I don't want to mention it. He was somehow allowed to teach a course to freshmen that year. By the way, he was never allowed to teach again because he did such a terrible job. But I was one of the guinea pigs. I was one of the students. So he rounded up all the physics students and asked us questions. And they were all yes or no questions. And all the people that answered incorrectly were kicked out of the room. So eventually only a few people were left, and I was one of them. So one of the first things he said to us was, never calculate unless you already know the answer. So I just came out of high school in Brazil, where I did not have the opportunity to take a course in physics. My school was very small. My class that I graduated from had 7 students, so I was one of the 7. So, but this was tremendous advantage in applying to universities in the United States, because if there are 7 students, there are 4 class positions. So almost everybody, more than half the class has a position on the application. There's president, vice president, et cetera, et cetera. So I never had the opportunity to take a course in physics. And there's a footnote here. Many physicists now told me that I was very fortunate because many people, not in Taiwan, I suppose, but in the United States and Europe, took physics courses and then were destroyed by physics in high school. So I never took physics in high school. So but I had studied some physics on my own, and I was completely puzzled because I thought physics was all about calculation. And how would I know the answer without calculating? And this is a very important point that Wheeler made. And Wheeler called it horseback physics. That was the term he used. But these days, of course, very few of us in this room ride horses for fun. But the whole point was that if you have to solve a physics problem while you're riding a horse. And so obviously you cannot calculate. You have to think about the answer in your head. So now when I first got to Santa Barbara, when I was offered a position there, I actually ran a seminar together with Frank Wilczek. And I tried to limit the number of equations postdocs are allowed to write down while giving a talk. I believe that I set the limit of 10 equations. The postdocs giving talks are not allowed to write more than 10 equations on the blackboard. Because I know, especially some postdocs would come in and start filling the blackboard with equations. But obviously that does not work. Most postdocs cannot do that. If you feel that if you understand something, you should be able to explain it in words. So the other thing I often tell students in Santa Barbara is to delete stuff and clean out their brains because they know too much. And Coleman told me the same when I got to graduate school. So Coleman was my graduate school mentor, and I was extremely fortunate because I was sent to Harvard to study with Weinberg. And I was so lucky because Weinberg had a fight with Glacier. And so Weinberg went off to MIT. And Steve Adler told me, no, you should not work for all these famous people. You should work for the youngest guy in the department and the guy without tenure, the guy with no reputation, because he's the hungry guy. He's the only one who's hungry. So, I worked with Coleman, and Coleman told me the same. He asked me, what did you learn as an undergraduate? So I told him what I learned, and he said, forget all that. Clean that out of your brain. I tell him something else. He tells me that's totally useless for particle theory, and so on. So what I found with undergraduate these days, of course, there's a lot of criticism, especially at University of California, because now for political reasons, we have students who don't know high school algebra. But on the whole, I would also say there are lots of students who know much too much, and their brains are completely cluttered by too much. So I'm always telling students to forget things. I invented this course for partly with these motivations. And instead of calling it Horseback Physics, I call it fly-by-night physics, as I taught it. And when I was writing this book, I, of course, looked at some of the books on the market that with the title back of the envelope calculations and so on, typical titles. And some of these books I find extremely uninteresting and boring because they were typically, you're given the formula and then you're just plugging numbers into the formula. But I'm not interested in my book, I'm not interested in plugging numbers in, but to derive formula. So if my books can be criticized, it's one of the things that people criticize is that there are very few numbers in that book. But when I was teaching this course, so I've now taught this course, as I said, invented this course about 7 or 8 years ago. So I have taught this course for 7 or 8 years, and I'm going to teach it again this fall. And I actually asked the students, have a survey to show by hands whether they want to plug in numbers. And nobody wants to plug in numbers. And they all said that I could trust them to know that they would be able to plug in numbers. So the other thing is that the book, there's no Fermi problems. When I was writing this book, a lot of people asked me whether I would have a lot of Fermi problems. So the classic example of a Fermi problem is when Fermi was at the University of Chicago, he asked people this question, how many piano tuners are there in New York? And then, of course, this is just a matter of multiplying a lot of the numbers together. And the trick is that every number is an estimate. And some of them is a high estimate, some of them is low estimate. But when you multiply them together, the high and low would cancel each other out. And you get a reasonable number. So this is also known as the Drake equation, right? Estimating how many civilizations are there in the universe. So my book doesn't have that at all. Now, commonly observed phenomenon, my other motivation is that in theoretical physics, there are many students, not all, of course, who get all A's in courses, but they crash and burn later in their research career. So getting A's is certainly a necessary but not sufficient condition. Okay, it's not sufficient. Of course, it's necessary that the top physicists presumably could get A's without any trouble. So, but that doesn't mean that if somebody gets C's all over, that he'll be a great guy. I remember when one of my sons was in junior high school or something, to go to these parents teachers conference where you meet the teachers and also the parents. And one of the parents told when this guy found out that I was a physics professor, he was very proud to tell me that his son got C's in his math courses and physics courses. And then he said he read somewhere that Einstein also did very poorly in school, which is, of course, completely false. It's a total myth. But then his logical reasoning was so advanced that he thought that his son getting C's in school means that he's going to be a great physicist. Okay, so it's certainly necessary, but not sufficient. So why is that? Over the years, I've observed this phenomenon because doing well in homework and exams are almost opposite to what is needed in research in the more cutting edge areas of theoretical physics. Of course, there are a lot of research in which the professors or your whatever your boss tells you to plug in and calculate and plug in and calculate or try everything. A lot of the research on superconductivity, for example, just try this, try that. But in the cutting edge area of theoretical physics, it's almost the opposite of doing homework and doing well in homework and exam, because when you do homework and exam, you already know what the appropriate methods are. So you know that if you assign the homework for this week, you know the methods you should use are the things that were covered in the course last week, and so you just have to plug in chart. So difficult part in research is, of course, to come up with the good questions, not to provide the answer. And I think it is probably fair to say, and this is something that I want students to appreciate, is that for every person in the community, I'm talking about theoretical physics, not experimental physics. For every person comes up with a question that moves physics in a new direction, there are probably tens or perhaps hundreds of people who could arrive at the answer. Okay, so an example of this, of a good question that nobody asked before, is, do black holes radiate? Okay, so Hawking asked this question, if you like, or what? And don't need to go into the history in detail. You can say Zeldovich, Penrose, and so on. But for every person who can ask this question in 1973, there are probably 100 people that are relativity experts, 100, 200, 1,000, who could work out that black hole radiation. Okay? People always think that students tend to think that the calculation is the difficult part. And of course, you open Hawking's paper, you see that there are like 20 pages of calculation, but that's not the hard part. The calculation that impress students are routine. So it's the question, the issue is to ask the good question. Let's see. Fuse about. So there are many famous stories and quips and quotes. So I'll tell you a couple more stories. So one is that when Sheldon Glacier, whom you guys know, because when I lectured in China a few years ago before the pandemic, every student there know about Sheldon because they told me there's some television program in which the main character is named Sheldon. And they also know that it's named for Sheldon Glacier. So as you probably all know, Sheldon Glacier got the Nobel Prize later for great contribution to physics. And he was also one of my professors at Harvard. When he applied to Princeton for graduate school, as you probably know, he and Weinberg both went to Cornell, and Weinberg got into Princeton, but he didn't. He was rejected. He told me he was interviewed by Wigner. And Wigner said, you know and understand all the equations, but you don't feel them. You don't. So this is how when I interview postdocs and students, I also feel that I have to get the impression. Some people know the equations, but they don't feel it. You have to feel the equations, for God's sake, okay? So basketball means throwing the ball through the hoop. I understand that, okay? But I cannot play in the NBA. But students, you have to have a feeling for the ball. Okay, so Glacier, of course, told the story and felt that Wigner was extremely unfair to him. But the list of all the people who did not get into Princeton for graduate school is a very long list and famous list. So Glacier is not the only one. Gelman also, for example. And so Gelman was going to kill himself when he did not get into Princeton, when he was rejected. but he decided not to, so that's a good thing. Now Dirac, I found this quote. It was actually quoted by Feynman. Feynman said that Dirac said the following. Dirac said, I understand what an equation means if I have a way of figuring out the characteristics of its solutions without actually solving it. So this is sort of similar to what Wheeler told us as freshmen. Okay, so I feel many students do the exact opposite. They don't feel the equation, but they know how to solve it. Yes, many people can solve equations, but somehow they're not Dirac. So here, let me start the physics of my lecture. So yesterday, my family and I went to see the movie Oppenheimer. And first of all, just to buy a ticket is so high tech that my wife had to figure it out. I would never be able to buy a ticket because you have to press some screen and so on and so forth. But what's extremely impressive to me was the movie theater was completely packed, absolutely full. And in fact, there were 5 of us and we got exactly the last 5 tickets. Now, interestingly, I got an email from Professor Chen in Hong Kong. Some of you may know him. He also went to see, because my wife told him to go see this movie. And he said in Hong Kong, there were almost nobody in the theater. Okay. So I also asked Yuan Zhiqiang from the Zhongyuan Yuan, because Yuan Zhiqiang and he's in Vietnam right now. So I said there must be a lot of people seeing the movie for Oppenheimer because Bobby was banned in Vietnam, right? It's not allowed. So he said that most people have never even heard of Oppenheimer. So the educational level in Taiwan is extremely high. To have the movie theater completely packed at the biggest movie theater in Taipei. So how many people here have seen this movie? Quite a few. Yeah, good. So you know what I'm talking about. So it turns out that chapter 6 in chapter 1.6 in my book is about this famous story about the atomic bomb test in Los Alamos. And there's a series of pictures from the Los Alamos National Lab. And let me see. Well, anyhow, I don't know if I could. Okay, that's the thing. You can see. So the famous story was that after the war, the British government asked the Americans to tell them how much energy was released and other technical details about the bomb. And the Americans refused to tell them, and the British were extremely upset. But on the other hand, there was a famous physicist in England, Taylor. And just at that time, some idiot in the American military released these photographs. And in a picture magazine, Look magazine. And in fact, as you can see, if I could figure out the pointer. Oops. Ah, 怎么回去? So as you can see in the lower left corner, it was the time. There's a timestamp. It tells you how many seconds after the explosion. Oh, okay. 这个 pointer 怎么弄? 你的 secretary email 昨天 email 给我说有 pointer 的。哦，这个好是 good， 谢谢。这里是吧？ OK， 谢谢。So as you can see, there's a timestamp tells you how many seconds after the explosion, and you can estimate for yourself the size of this fireball. And the famous story is that Taylor was able to figure it out using almost high school level dimensional analysis. Okay. So the fireball from an atomic explosion pushes the ambient air outward. So the outside air is just the usual density of air, and here's the radius. And then we just use the high school dimensional analysis. Energy, I use square bracket indicated dimension, is mass times kinetic energy, ml squared over p squared. Density is mass over L cubed. And we want a relationship between R and T, between the radius and the time. And we need to get rid of m. So therefore, you see the only way to get rid of m is to divide one by the other. When you divide, you get L to the fifth of p squared. So this is a very interesting formula, actually, because in physics, we almost never have 1/5 law. This says actually the radius goes like the energy to the 1/5. And with time, it's 2/5. So it's a 2/5 growth, and you can just plot on the log-log plot, and it verifies the 2/5 growth. So this dimensional analysis, not only is it so simple, but it's built in, has a built-in check. You can actually verify that it goes like 2/5 growth, and that gives you a lot of confidence. So this is also a quick check when you do dimensional analysis. You always just check that. The radius R grows with time. As time increases, it grows. And the larger E is, the larger R is, so on. And the other thing that is mysterious in this world that I always find very, very mysterious, which is to understand the number 3. So in physics, we only need 3 fundamental dimensions that for mass, length, and time. And 3 and only 3. So this number 3 seems to pop up everywhere. Okay. So it's not a blind dimensional analysis, but educated dimensional analysis. So I'm sorry, when I was preparing these transparencies last week, I don't have any technical support at home here in Taipei. I can go down the hall and ask some postdoc or some computer guy how to do this. So my transparency is a little bit primitive. It's just copy and paste it from my book. Okay, so when you first hear about atomic bomb blast, you might think that we need to master some nasty bit of nuclear physics. That's the reaction of a lot of people. But in fact, the job of nuclear physics is just to produce the energy. And once the energy is produced, its job is done. You don't care. Now, the only thing that is required is that the energy is produced almost instantaneously in a region much, much smaller than now. So there's a length scale and a distance scale, a time scale and distance scale, in which the nuclear physics operate. But they're both essentially 0, so we can forget about them. That's absolutely crucial, right? Because the dumb people would write down all the things. That's what the dimensional analysis books I looked at when I was writing this book. It said the first step, it typically gives you 20 steps, step 1, step 2, and so on and so forth. Step 5 is probably go to the restroom or something. But step 1 is write down all the variables. And typically you write down 20 variables, and that's of course wrong. You only write down the essential ones. Now next, some people might think that all kinds of complicated fluid dynamics, that shock waves, and so on should be involved. That may be so, but ultimately the blast just generates a ball of hot gas whose purpose in life is to push the ambient air outward. Okay, so it's just a ball of hot gas. So by the way, a lot of physicists, just this morning I was getting emails from all over the world about the movie that people have seen. And so theoretical physicists are really nitpicking types. So there are a lot of nitpicker types. Nitpicking you can do. One nitpicking is that one physicist wrote to me that he was very upset. It's called atomic bomb. It only confuses more people. It should be called nuclear bomb because the process is not atomic process at all. But the other thing that I learned when I was writing this book is that the Russian, this guy at Boston University, this Russian guy, by the way, very smart guy. He told me that I shouldn't call it fireball, but that's what everybody calls it, including Los Alamos. So in some sense, there is no fireball. It is a fireball, all right? But there is no fire. It's just a ball of gas. There's no fire inside. So just to make sure you understand. So let me now go through. I have a lot of transparencies to give. And the second and third lecture will be on the blackboard rather than transparency. And then I hope to go at a slower pace and then answer questions and go into more details. Okay, so dimensional analysis, as you know, I was really surprised that dimensional analysis was not explicitly practiced until the late 19th century. But the most famous example goes back to Galileo. We all know that that period was simple dimensional. That shows that it's square root of L over G. So you should do the following experiment. You should try to explain this to some famous professor in the humanities, and they will be amazed. Okay, it seems like we get an answer from nothing. The humanities were amazed that you can get this answer without doing anything. But it's not true. A lot of profound physics are actually hidden, right? So for example, you get the fact that it goes like the square root of the length. You double the length and you make the length 4 times as big and you double the time. Okay. But the profound physics it hides, of course, the inertial mass is equal to the gravitational mass. The 2 masses cancel out. And that's, of course, the basis of Einstein's theory of gravity. So I think it's not an exaggeration to say that after Galileo derived this formula, for the next 300 years, the only person who understood this formula was Einstein. None of the other people understood. Not okay. So the goal of fly-by-night physics is not to get numerical agreement. That's what I tell the students when I give this course. But on the other hand, after you get the answer, then you should calculate. And then, of course, in physics, we want to get the exact answer, okay? But that's another course that I'm concerned about. So with some experience, you can even get the factors of 2 pi's. So the formula I just wrote on the previous transparency numerically is off quite a bit. But with experience, you know enough physics, everyone in this room know that you should use circular frequencies versus the everyday frequency. The everyday frequency that the guy walking around the street uses is how many cycles per second. But in physics, we have circular frequency. And you can think about it because sine and cosine. And so there, right away, there's a 2 pi. So then with the 2 pi, then we agree much better. So it's not a question of getting numerical agreement. But on the other hand, you can get a lot of the 2 pi's if you think about it. And interestingly enough, even the 2 pi's in quantum field theory, you think there's a trivial example on pendulum. But if you think about quantum field theory and you do Feynman diagram calculation, you see there are a lot of 2 pi's. 2 pi over 4 is in every Feynman diagram. And Schwinger's famous thing in which he beat Feynman is, of course, has a pi, the alpha over pi. If you can say Schwinger beating Feynman to see who can find the pi first. Long time ago, this was probably 30 years ago, I had dinner with an extremely distinguished condensed matter theorist. He's now retired, but he's one of the most famous condensed matter theorists in the world. And we were talking about physics, and he was very puzzled about dimensional gravity. About dimensional analysis applied to gravity. I think we were talking about Hawking's radiation. And he, of course, like the standard textbooks, counted all the variables. And he said there are too many variables. You cannot do dimensional analysis. But here's the secret about gravity, okay, that I emphasize in my book. Capital G never occurs alone, okay? I don't know how the students, what they realize. Have you ever seen a formula in which there's only capital G? No, it always appears with a mass because it's meaningless to have capital G. So using equating acceleration to the force, you see that this combination GM, which I call kappa, has the dimension L over T squared, right? From the that you just use this formula, L cube over T squared. Okay. So kappa is the thing that appears all the time. And important, I ask you to remember, it's length to the cube to time to the second power. Okay. Now, then using this fact, you can derive Kepler's law in 5 seconds, literally 5 seconds. Okay. So that kappa, as I kappa is the GM, and m being the mass of the sun. And suppose we want to calculate the period of a planet going around the sun in a circular orbit of radius r. So you would, the good student, your friend, who's the guy who gets all the A's and so on. By the way, this is exactly my experience in Princeton when I was an undergraduate. I had a friend who always gets A plus in all his exams, no problems. I never get A's and A plus. But I can admit that without being too arrogant, I would say my career later is much better than his. He gets all the A's and A plus. Okay, so your friends that gets all the A's and A plus, they'll calculate. And maybe that friend is so good that even he can solve some differential equations to determine the motion. But you know that after the dust settles, it has to agree with dimensional analysis. But since we pointed out that kappa is L cubed over T squared, how can the relationship between the radius and the period of the planet going around R and T, it has to be R cubed times kappa T squared. So you derive Kepler's law in literally 5 seconds without sweating at all. So I always talk about sweating because one of the things that Sidney Coleman told me when I was a graduate student was that I'm not allowed to sweat. If you want to be a theoretical physicist, you should not sweat. So he said one day, early in my career, I was very proud. I think I spent a few days doing a calculation, and I had like 30 pages of calculation, and I showed it to him, handed it to him. I was very proud. He looked at the calculation and flipped through it, and then he puts it down. He said, well, you spent a lot of time calculating. You must have sweated. And then he said, and this is a little bit sexist, but I don't see many women in the room. He said to me, and this is almost exactly the tone. He said, theoretical physics is a gentleman's diversion. Tony, if you're going to sweat, don't do it. Okay? So I think that's the right attitude. Okay? So, of course, you can secretly do thousands of pages of calculation. So, okay, I'll tell you. Well, that's a separate story. I won't tell you. We went snuck into Feynman's bedroom and discovered that Feynman wants to give the impression he doesn't do any calculation. He knows the answer. But then we discovered there's like at least 30 pages of calculation in his bed. See? So if we apply Kepler's law, we all know that Kepler's law works extremely well. And the farther away from the Earth, the orbits are a little faster. And the Mercury, this is why Mercury is called Mercury, because Mercury is the god of the peace and travels. Mercury moves the fastest, and Einstein understood this. And that's why Einstein used Mercury, the precession Mercury. Now, at this point, I say something about fly-by-day physics. It turns out, much to my surprise, also when I was studying all this stuff, reading many books, that Kepler's law also holds for highly elliptical orbits at 5 degrees Fahrenheit. So it's not obvious at all that Kepler's law. And I cannot think of a good fly-by-night argument. It has to be fly-by-day. It requires sitting down and doing the calculation. So now I know how to do the calculation because I spent 2 weeks doing it. And it's non-trivial because when you have a highly elliptical orbit, of course, eccentricity comes in. It's not just a circle. So it's not just dimensional analysis, but it's a highly non-trivial result. Okay, so from the precession of Mercury, you know, Einstein also has the deflection of light. So a precise calculation of the angle in which light is deflected, that may be found in many standard textbooks. But let's just use dimensional analysis. And again, the key is that, and this is what the famous condensed matter guy missed, is that G and M do not occur separately. They're only in this combination. So then you have GM and C and the radius of Mercury's orbit. So this is the precession of Mercury. So the angle by dimensional analysis has to be this. Now, there's one thing dimensional analysis doesn't care. It doesn't care if you're Newton or Einstein, right? So both Newton and Einstein has to get this, except the numerical factor out front. The numerical factor out front is a factor of 2, it turns out. Isn't that amazing? I find it's absolutely amazing that one, Newton and Einstein, they differ by a factor of 2, okay? So this was one of the challenges once I heard Schwinger give a colloquium. And Schwinger's colloquium to the audience, Schwinger's colloquium is very interesting. It's different from other colloquium I've heard. The Schwinger walks into the room and he doesn't tell the audience anything. He just tells the audience all kinds of puzzles and you guys solve it and see who can solve it. So that's where I first heard it from Schwinger. Can you understand this factor too? Okay. So that's obviously not fly by night, but fly by day. I can tell you the answer in words that I now understand because I wrote a huge thick book on Einstein gravity. And one reason is to understand why there's a 2. And the 2 is very simple. That's because Newton curved, when he curved space-time, Newton only curved time. And Einstein curved space and time. So that's a factor. Okay, so if you can, you can understand that, you can understand that. Okay. You won't be, most of us are not riding horses anymore, like Wheeler's Horseback Physics. But we all ride on buses and airplanes and so on, especially airplanes. And then when you're sitting on the airplane, not able to go to sleep, see if you can calculate this factor 2. Yeah. Okay. So we all know this Mitchell-Laplace criterion for black hole, which is, and you can see that it comes out immediately in one line from this, because it's when you have a black hole, the deflection of the light and so on is given by the same formula. It has to be all the one, and then there's a black hole. So the next thing is the next topic in my book was the Bohr atom. Now, Mr. Bohr, so I used this Bohr story to tell Bohr the difference between Bohr and an extremely good student at University of California, Santa Barbara. Okay, UCSB, the top. Bohr was faced with 2 unknowns, right? Because he was saying that the atom, the hydrogen atom, let's say, is the same as the solar system, like the planet Earth going around the sun. So there are 2 unknowns. There's the velocity of the electron and the radius. But he had only one equation, which is centrifugal force balance against attraction. So classically, it's correct that there's only one equation because you can either, V and R are not determined. Either V or R is set by initial condition. If the thing starts moving faster, the radius adjusts, or, you know. So this is a great example, I think, in the history of physics. It's not just one wild guess. It's one wild guess leads to another wild guess. And they're both great. They're both Nobel Prize winning wild guesses. Okay, so we had to go back to Planck. Planck tried to mimic the Maxwell-Boltzmann distribution. Okay, so Maxwell-Boltzmann wrote down this distribution. So if you try to mimic this, that was Planck. Planck was desperate, of course, because he was number 2 on all the job lists. He was very worried that he was not going to find a job. And you guys all know who the number one on the list is at the time. It's of course Hertz. So Hertz had discovered electromagnetic waves, and Planck has not discovered anything. So Planck finally found a job, but the reason he found a job is because the job is not purely physics. The job for that job he was required to repair the organ in the church. So that was anyway. He tried to copy Maxwell-Boltzmann and write down for the frequency distribution this formula. But the dimension is wrong, right? So the temperature is an energy, and it's a circular frequency omega of the wave, okay, is inverse time. So how can time and inverse time and energy be related? So Planck called it an act of desperation later. He said this was an act of desperation. He was absolutely desperate. The two quantities that he wants to relate are the same dimension. So you and Planck have to be bold enough to invent a brand new fundamental constant, which h bar, of course Planck had h, but I have h bar because of the 2 pi, it's more convenient. So the h bar omega is the same dimension of T, that of energy, okay? So the thing that I care about, we all know that Planck's guess was correct, okay? So just making a completely wild guess, with no logic, no reason, nothing, just a guess, okay? You get reduce that h bar as the dimension of energy times time. Okay? So therefore, you can also ask, what is this function? What is this distribution? Planck distribution. So students often ask, well, we have some really dumb students. This is the dumbest of the questions ever, which is how did Planck derive the Planck distribution? Derive? How can he derive? From what? I mean, he was the one who invented quantum physics. How can he derive anything? That's the problem. The students that come to Santa Barbara, they all thought that physics should be derived from something. Everything is derived, everything is logic. Come on. What finally said, get out of this room. The math department's over there. Then you can derive everything. So what can he derive? How can Planck derive from what? You know, from his mother's birthday or what? You know, so this is what I tell these dumb students. So what he did is he knew the behavior of the distribution of both ends, right? At the high frequency and low frequency, and then he guessed using what this guy called the Dou function hypothesis, chapter 1.4 in the book. So in my book, I from my experience as a physicist, I realized all the functions, almost all the important functions in physics are very boring and very dull. They're just typically some power, maybe a square root or something. So some exponential here and there. It's never some crazy functions that undergraduates think you should learn. Most functions in physics are very dull. And in particular, if you know its limiting behavior at the two ends, in many cases, almost obvious what it is. So Planck was able to guess this formula. And unfortunately, I can't even see it under this orange from the something. So from the Planck's guess, we go back to Bohr. So Bohr was sitting around. He has two unknowns for one equation. So for the atom, he needed one more equation, right? So then what he did is he then remembered what the dimension of Planck's constant is. And I think this is one of the most important calculations in physics, in the history of physics. As I told you, the dimension of h bar was et, Planck's constant. Now E is ml squared over t squared, kinetic energy in freshman physics, times time. Okay, so that's ml squared over t. But the important thing, the clever guy, so this any average student could get to. But this is what the top students. The top students separate themselves square. One L will be the L. Then that's what somebody can find. I would be stuck in right? So you put the L, you split the 2L and you see this is velocity. And then you see that mass times velocity times length. So it's dimension angular momentum. So Bohr has asserted that the angular momentum of the electron is equal to constant. So this, I think, is this equal sign to me one of the most important calculations. And Bohr was extremely lucky when he plugged this in. So he said the angular momentum has to be equal to h bar. So he got the right answer, including the factor of 1/2. It's amazing. So it just, I rank all the people in physics about how lucky they were, and Bohr has to be top of the list. Einstein was not far behind because of World War I helped Einstein a lot, right? And so the other thing is the importance of using the appropriate units, which I will skip over. But anyhow, but we now know Bohr's derivation is completely wrong. It's total nonsense, right? Every student can tell you the angular momentum of the electron in the ground state of the hydrogen atom is 0, not 1. So he's got the other equation. He needed 2 equations. So the other equation, he just guessed that the angular momentum is equal to 1 in the units of Planck, in Planck units. But now any dodo students in the quantum mechanics course, the people getting D's and E's and F's or whatever, every bozo can solve the hydrogen atom using Schrödinger's equation. Is anybody impressed? No, nobody's impressed. That's what I tell my students in my class on fly-by-night physics. So tell me, stand up all the people that know how to solve the hydrogen atom using Schrödinger equation. Wow, I'm so impressed by you guys. So I'll immediately write a letter. Well, anyhow. So in fact, when Bohr published his paper, there was widespread skepticism. Otto Stern, who was famous for the Stern-Gerlach experiment, and Max von Laue, the two of them were young students at the time, or young guys at the time. By the way, both Stern and von Laue got the Nobel Prize later. And von Laue we like a lot because he was one of the protectors of Einstein under the Nazis. So the two of them took an oath, 中文好像叫发誓是吧? That they would quit physics. 他们两个学生发誓 if this nonsense of Bohr would turn out to be right, okay, we will quit physics. Okay, and this oath was based on this famous story of shooting the arrow off of his son's head. And so I asked the students in my class, how many times have you guys taken an oath that you would quit physics? So people don't have this spirit. Now, Nambu told me that when I was talking to Nambu, unfortunately, Nambu has passed away. He told me the story, which I have not seen anywhere else, so I may be spreading a false story. But if Nambu told me, it may be true. At the end of the war, as I already mentioned, there was a race between Schwinger and Feynman on calculate G minus 2. But don't forget Tomonaga. Tomonaga was also racing to calculate G minus 2. And Tomonaga had a student, Koba. And Koba made a mistake, and he got the wrong answer. And Koba later became a fairly famous physicist, fairly substantial physicist as well. So according to Nambu, Koba went to, being Japanese, right? Koba went to Tomonaga and offered to do harikari, kill himself. And Tomonaga told him he could just shave his head instead. So, but, I would be so impressed by physics in Taiwan if a student would commit harikari if they did a wrong calculation. I'm not recommending it. I'm just saying I'd be really impressed. In fact, I would be the first one to stop the student. You shouldn't. So everybody makes mistakes. So Feynman makes mistakes, Fermi makes mistakes, everybody makes mistakes. So if you make a mistake, don't commit harikari. But you should have some spirit in you, like Stern and von Laue. You should say, if this stuff is correct, then I will quit physics. Right? This is total nonsense. I mean, people don't, you should have more opinions as students. So, using the Bohr atom, using the so-called Bohr nonsense, Victor Weisskopf, I've heard about it for many years. It's in fact based on an earlier work of some German chemist, which he famously was able, by this hand-waving fly-by-night without doing any calculation, he was able to account for the properties of the atoms in the periodic table up to neon and beyond. This is chapter 3.4 in my book. So the two questions I could ask the students, which atom is the smallest in size? And which one is the second smallest? Okay. See if you can do it if you've never seen it before. Okay. It's not a question of sitting down and, oh, I'm an expert in solving Schrödinger's equation. I got an A in some course in quantum mechanics. But see if you can answer this question: which atom is the smallest, and which is the second smallest? So, well, think about this. So, there's also, physics is full of apparent paradox. And I want you to try the following experiment. Next time you run into a physics student, or even better, a physics professor, and maybe not a experimentalist. Experimentalists know a lot of physics. But ask a theoretical physics professor, ask him or her this question. The electric field around a charge falls off very rapidly, like 1/r squared, right? They're out the distance from the charge. So how is the electromagnetic radiation possible? Every day we turn our cell phone and get out my cell phone, there's the electromagnetic waves transmit information all over the place. I get emails from my friends. So how can electromagnetic wave propagate over long distance? Even granted that some amplification is usually needed after detection, of course, the signal will be very small and you need to amplify. But still, for sure, it doesn't fall off like 1/r squared, right? You know that, in fact, it falls off much slower, like 1/r. So can you figure it out? So I've done this experiment. You ask a lot of theoretical physics professors and see if they could answer this question. So then I had a lot of fun writing this book and also inventing this course. So one of the professors who would, of course, know an answer, but he's not a theoretical physicist, experimental physicist, Ed Purcell, I think he was the greatest physicist at Harvard when I was a student. He was a great experimentalist and received a Nobel Prize and all this. He deduced the existence of radiation for uniformly moving charge suddenly brought to rest. And what he used was causality. He said that if you have a charge moving along, okay, and it suddenly stops, you bring it, it's like a car crash. The observer very far away, he does not yet know the charge has stopped. So he knows about electric lines. So he thought the charge is over here, the observer is over. So he thought the electric lines of force should come here. But in fact, the charge is over here, and the electric line of force is coming out here. So it has to match. Physics is continuous. So it's a kink by continuity. And it's that kink that produced enhancement. Okay, so this is chapter 2.3 in my book. And of course, this is explained in Purcell's book. But Purcell said he's not the first to think of this argument. In his book, he actually cites a guy by Lane. By the way, if you want to understand electromagnetism, you really should read Purcell's undergraduate textbook. Unfortunately, that book has been watered down and destroyed by some idiot. So the thing is, nobody's impressed that you could solve Maxwell's equation and obtain electromagnetic radiation. It's a century and a half already after Maxwell. The question is, can you think of this kind of Purcell type argument? Okay, so a student that could think of that would impress me. So here are a lot of challenges for students. Suppose you only know how to solve the, yeah.
I knowledge very well. It was Sheldon Thompson.
But besides the guy named
Really?
yeah.
But Thompson had really quite detailed. Well, Thompson was a theory.
Well, I'd like to present this from context.
Yeah.
Thank you.
And the second thing is that he said that Maxwell himself didn't know that a shaken charge would emit.
Right. I see.
Because he did not agree with or he did not see the happy solution.
So it's causality. When you say retarded, it's the argument's based on causality.
And the solution to Maxwell's equation is given by A and phi and particle form.
Right.
And that was given by Riemann and Lorentz. The Lorentz is Lorentz without
I see. Yeah. By the way,
Maxwell. But Maxwell somehow disliked that or whatever. I could not know the theory, but he did not appreciate Riemann and Lorentz. So, so it seems that people thought that maybe Maxwell himself did not realize that his solution allowed a shaken electron That's why I never tried to find because you think that once Maxwell realized that he should himself think the experiment to find the radiation.
but he was able to solve this equation in free empty space, though, right? To find a wave, yeah. But not the radiating from it.
Yes.
Right. Because you.
So it was not trivial, when you say that, you can, just solve Maxwell. No, even himself may not be able to do that.
No, but absolutely, because then I think that's a well-known phenomenon in physics, because even the great people, the real greats, cannot possibly do everything, right? So there's room for the dumb people like me to come around and still have a few things left to do. And I think that's true in Maxwell. Like, for example, you can always ask Poynting vector. How could Maxwell not know? I mean, let's say he doesn't know how to do radiation from a charge, but he could do the propagate. He could certainly solve the propagation of a wave in empty space. But then you have to ask, how's the energy momentum transfer? How come he doesn't have the Poynting vector? This is the same. How did Einstein not have the Schwarzschild solution? And you know how Einstein doesn't have the Schwarzschild solution? It's because he was solving the space-time around the mass. And Einstein is a very original guy. I would say if we give this problem in a course on general relativity to the students, I'm sure 99.99% would use spherical coordinates, which around some spherical distribution of mass. Einstein used Cartesian coordinates. And that's how he missed Schwarzschild solution. Right? And by the way, Schwarzschild solution is also another piece of luck, because if a Haidar student were trying to find a Schwarzschild solution, I don't know if the modern Haidar student do that, because it's in World War I, trenches by artillery fires and so on, no air conditioning. That Schwarzschild was able to find a solution. But Schwarzschild paper was totally not logical. I actually looked up his statement, and he said that there are not enough equations in Einstein's theory to determine that. So he invented an extra equation. So the extra equation he invented was the determinant of G mu as equal to 1. But it so happened by chance that its solution fits that equation. So it's complete. We now know Einstein had too many equations, one more, one of them is beyond that. But Schwarzschild thought there were not enough equations. So this is also why the people that get A pluses with things very logical, they should go to the math department. Do us a favor, go to the math department. Because the people count how many equations, they have not enough equations, and the history of physics is full of such crazy stuff. Okay, so I now go to quantum mechanics in chapter 3.2. I'm jumping from electromagnetism to quantum mechanics. And here are the challenges for students. Suppose you only know how to solve the energy spectrum of the infinite square well. So can you invent a fly-by-night approach to get the energy spectrum of the harmonic oscillator, of the Coulomb potential, and so on? So remember, I don't know, maybe I shouldn't say this in Taiwan because students in Taiwan are supposed to be so smart. But I certainly say this in the United States, in Santa Barbara. So really, any bozo that gets A's in quantum mechanics course could solve the Schrodinger equation, right? To get the exact fly-by-day answer for harmonic oscillator Coulomb potential. Any student can do that. But the question is, can you do it by fly-by-night without solving the Schrodinger equation, just knowing how to solve this energy, just knowing the energy spectrum of the infinite square well? And in my book, I claim you can, because you can solve this, the infinite square well already. And the harmonic oscillator is sort of a little bit curved. So what's the difference? You know, one is sort of like this, and the other is sort of more curved. So, okay. So another thing is stellar burning. Stellar burning works like this. Okay. This interests me a great deal, and because I read it when I was a postdoc or something, and stellar burning involved two protons approaching each other. Okay, so the physics is something like this. There's a Coulomb repulsion between the two. Sorry. Okay, so there's a Coulomb repulsion between the two protons, right? They cannot approach each other. And then when they get very close to each other, arms or hand, that's when the process takes time. Then the two protons, the weak interaction kicks in, and then the two protons, that's whatever they do, combine and feed, etc., etc. So the radius of closest approaches is our A, there is some energy. Okay, so this is just a sketch. This is vastly not to scale because the scale of the nuclear reaction and Coulomb repulsion is many, many orders of magnitude. This peak would be on the next floor. And so the energy is very low, and how do you get through it? And Gamow had this great idea of tunneling. And by the way, his autobiography is one of the most interesting ones that I read ever, because he was inspired by his escape from the Soviet Union, how you tunnel out. So, so this is a difficult problem at the time. And of course, but nowadays, I think physics has sort of degenerated. Nowadays, if you show this problem to any student, no problem. I'll give you the answer in 2 hours. I'll just turn on my computer and just plug in and just numerically crank away, right? So, and then that generation's already maybe obsolete. The even younger generation just ask a chat GPT what the answer is. Okay, just it. So, but what Gamow and I did, I think it's a great example of fly-by-night, which is just replace that. Who cares that this thing is curved like this? You know, the basic physics is just that it's just some barrier that the proton cannot get through, and then nuclear reaction kicks in. And so by the way, I always thought that, you know, the people say that he didn't get the Nobel Prize because he was an alcoholic or something, but this is absurd. Nowadays, moral behavior doesn't matter at all. You don't have to be a moral person. You can be any person and get the Nobel Prize. So, so he should have gotten a Nobel Prize for tunneling and for Big Bang cosmology. So he replaced the curved potential we had by this constant potential. Now, constant potential, of course, we can solve, and nowadays, of course, as I already said, you can turn on the computer. So of course, you expect it to do much better. So Wheeler should be modified. When I talk to the postdocs, who newly arrived, never turn on your computer unless you already know the answer. So maybe is the new version we learned. And in fact, this reminded me, during the early days in Santa Barbara, when the Institute was first founded, the director of our Institute, Bob Schiffer, he tried to prohibit computers. And he said he came here to think. But of course, he failed totally because all these people were yelling and screaming. All the young people that they know computers, they're going to bring their own computers. They write back to their home institution and ask the secretary to ship the computer over, and so on. So Bob Schiffer had to give in. But I could tell you a story about Hans Bethe. So Hans Bethe, I think he was 90 something and he would come to visit quite often. He would show up in Santa Barbara. And his office is down the hall from me. And one day I even got a note from him that he wanted to talk to me. I've completely forgotten what he wanted to talk about. So I thought, oh, this Hans Bethe, this old guy, he didn't complain about not having computers. So I went to see his office and he was doing some stellar calculation. You know, late in life, he did a lot of stellar astrophysics. And there he was sitting in his office and he was with the slide rule, he was going back and forth and he was perfectly happy. And he was able to publish papers. So, but now, of course, everybody has computers and so on. So I was going to have an intermission because this talk has gone on for too long. So that was my plan. I guess it's how much time? A little over an hour, right? Hour and 10 minutes. So I'm going to have an intermission. And during the intermission, you know, I could go to the bathroom or wash my face or something. But during the intervention, I assigned 2 problems to the students. So the first problem is just math. But given a triangle with size, length, the length of the 3 sides A, B, and C determine its area. Second problem, I think that problem, I think it might be invented by Lambda. Schrödinger, 1 dimension, okay, Schrödinger equation, 1 dimension. Here's the potential. The potential is arbitrary, and it has a lot of bumps. And there's a parameter G that I put in front of the potential. And of course, in general, I cannot find the binding energy. But can you guess what the binding energy is as G goes to 0? Can you find a formula for G? Okay. So I'm even willing to give you a hint. So to solve the 2 problems, okay, first, you have to use your brain. And 2, you have to use dimensional analysis and guessing. Okay, so here are the problems. And I don't need to go to the bathroom, but still maybe I should just roll with this. So I guess I have another half an hour still, right? Okay. Good. So I'll be back. Okay, I'm back. Okay, I'm back. First of all, I should apologize to mathematicians. When I was in the bathroom, I ran into a mathematician. So, but anybody who's read my book, you know that I'm very, very harsh on philosophers, and even much harsher on the philosophers than on mathematicians. And last year, I was totally surprised because some philosophy professor emailed to me. He wanted to come to Santa Barbara to talk to me. I was absolutely amazed. And I said that, aren't you, when I met him, I said, aren't you bothered by the fact that I'm always making fun of philosophers? He said, no. He said, you and Feynman are the worst. In both of your books, Feynman and you always make fun of philosophers. But in your own way, you are very philosophical. So I was very amazed by this. Anyway, I hope that students have been able to solve these two problems. Show you the answer. So first problem, I'm sorry that this orange thing. Oh, maybe I could. Can we click on this and get rid of the? It says 停止这里. Okay. Well, okay. So here's the solution. So the ABC are the length of the two sides. If A plus B is equal to C, then of course the triangle collapses. The area should be 0. So therefore, the area should be proportional to A plus B minus C. But by permutation symmetry, the three sides are the same. So it should be this times B plus C minus AC plus C. And if A plus B is actually less than C, then the triangle doesn't exist. Right? And math should be intelligent enough to know this. So therefore, the simplest way in which things doesn't make sense in physics and elementary physics and mathematics is square root. So there must be a square root of this thing. So we should be looking for a formula for A squared, the area squared. So then dimensional analysis. A squared has dimension L to the 4th. So this is dimension of length to the 3. So we must multiply Q by a length. But this length must be permutation invariant, right, by symmetry. Therefore, it has to be A plus B plus C. So A squared is equal to this, right? Then some overall constant that we don't know. We have to determine the overall constant, but we can just consider one special case. And the special case is A equals B and C goes to 0. So it's extremely narrow isosceles triangle, okay? To which we know that the area is just AC times 2, and then A squared is square. And from this, you immediately, instantly get the coefficients 1 over 16, okay? So I like this a lot because it sort of embodies the finite physics, the spirit applied to math, okay, to apply to elementary mathematics. In fact, this also provides one more proof of Pythagoras' theorem. So the simple way of doing this problems, of course, that most students would do is to drop the vertical and then use Pythagoras theorem to determine the vertical and then figure out the area. But when you do that, you destroy the symmetry of the problem. The ABC should be, if you use C as the base, then C is privileged, okay? But after we get this formula, for example, you can use it of all kinds of things. You can assume that the triangle is right angle triangle, and then you get Pythagoras theorem. Okay, the other problem is what I call a Landau problem. And there's some very bumpy potential. So we start with the Schrödinger equation to determine the binding energy. And the typical reaction is, how is this possible? When I was a student, when I first saw this, I was not a student. I think I was an assistant professor when I saw this. I was amazed in Landau and Lipschitz's book. How can you solve this quantum mechanics problem? So, how is this possible? Well, the answer is the following. You have to think like a wave function. Okay, you have to feel it. That's what I said earlier. You're not solving Schrödinger equation. You have to feel, as Dirac and Feynman and all these people told us, you have to feel the equation. So you have to think like the wave function. The wave function is exponentially decaying outside, but inside is cosine kx with some wave number k. But as the potential becomes shallower and shallower, right, k is going to 0. So the cosine, the wave function inside is flatter and flatter. So it does not sample all the bumps, okay? So wave function doesn't even know that there are bumps. So this is the secret why you can get a formula. Now, the other thing that's very important about physics is physics feeling. It's classically, just think, what would you do? Okay, classically, you would sit at the bottom of one of this potential, right? So suppose you're sitting there, classically, your model. Then the binding energy would fall to 3. But in quantum world, you are spread around. You have to be bouncing around for Heisenberg. Heisenberg is going to say, you don't know where you are. So this means it's much more loosely bound, right? It's not all the G. It has to be smaller than all the G. So you're guessing that it's all the G squared. And once you write down all the G squared, and you know the fact that you don't sample the bounds, so the only quantity that come in is the integral dx e of x, and then you sit down and work out this. So now, one of the lessons from this example, there's a universal formula. Now, so the question is whether you're a mathematical type or not. So when I first saw this problem in Princeton, and I told this to some guy, some mathematical type, the mathematical type was immediately able to do some more work and publish a paper and so on and so forth. So the question is whether you're a mathematical type or not. I'll tell you what a mathematical type would do. So a mathematical type would immediately think of something to do. But what I want to know, what I want to say is what you would do in research. See, these examples are, of course, elementary, using elementary things, elementary quantum things. But if you're doing research in a cutting area in which you don't know what's going on, if you have to solve a problem like this, what would be the tactic? The tactic would be to work out something you know how to do, which is finite square well, using fly-by-day method. So, which you can also use do bi-dimensional analysis. Then you just regard this as an applied math problem. And once you work out the finite square well, you can then see how the problem goes. Okay. So now my time is almost up. I want to talk about one second most important paper. Most theoretical physicists have written the number of important papers most theoretical physicists have written in their career. 99.99% is exactly 0. The great ones have written 1. Okay, Einstein has written something like 7. Planck has written 2. So Planck's second most important paper is perhaps not widely known. But this is what Planck said. In a tremendously insightful paper, he pointed out that these 3 constants, G, C, and H bar, because he introduced a new constant, which in order that we finally have a universal set of units for mass, length, and time, the three basic units in physics. So we would like to base our physics on something important, not ephemeral. And when I talk to some, certainly not somebody's foot, but when I talk to some physicists when I was writing this book, they say things like, well, how about the mass of the proton? You know, but even the mass of the proton is ephemeral because in the early universe there may be no proton. The proton could have broken up into quarks. So you want physics not to involve provincial human-made units, such as ham. By the way, that is a unit, ham, but probably not used very much. So if I teach a freshman physics course, I will ask students to convert all the meters in a book into hands. There's BTU or degree and things like this, right? So this is Planck's great contribution, and this is taken from Planck's paper. Okay. So this is literally what he said. He said it offers the possibility of establishing a system unit for length, mass, and time, which are independent of specific bodies and materials, and which necessarily maintain their meaning for all time and for all civilizations, even those that are extraterrestrial and non-human. That's what Max Planck said. So at that time, this was quite a shocking statement to make, and he was mocked by idiots. For example, Mach. So Mach is my top of my list of idiots in the history of physics. So Mach also was famous for mocking people, and he's the one who drove Boltzmann to hang himself, right? So he also made fun of Boltzmann. So that's his secret. So according to according to Planck, we have three natural units, and these are now called Planck units. So one of them, they're just given here. I won't go through them in detail. There's the Planck mass, and then the Planck length and the Planck time, and they all form of these three basic constants, h bar, g, and c. And three units and three great names, Newton, Einstein, and Heisenberg. Another way of saying this is that in these natural units, with c equal to 1, g equal to 1, and h bar equal to 1, the system of units would be understood no matter where your travels may take them, within this galaxy or far beyond. And this brings me to what I call the cube of physics. So physics consists of these three fundamental constants, h bars, and it turns out instead of c, it's more convenient to talk about c inverse and g. So we start at this corner. At this corner, there's no gravity, Newtonian gravity, and there's no c inverse, and there's no h bar. Okay, so all three of these things are zero. When you turn on g, you get the Newtonian gravity. And when c inverse is zero, but you turn on a finite c, then you get to Einstein. And you turn on h bar going in this direction, h bar is zero here, then you get quantum. And from this corner, you get the quantum field theory. And from Einstein special relativity, if you turn on capital G, you get from Einstein theory of gravity. And then here, this corner is not very well known, but it's also quite interesting, which is one of the quantum mechanics in the presence of gravity. And finally, in this corner, we have quantum gravity, which is what people are trying to, a lot of people, not everybody, definitely not everybody, trying to get to. Okay, so now I want to show you that to fly-by-night physics, Planck's units are extremely useful because we are sort of get to the essence of physics. We don't have all these crazy units to worry about. So imagine a box of photons, and the volume of the box is V, and the temperature is T. So temperature in these units is an energy, which is and the mass, which C1 is mass, which is an inverse length. And the volume is, of course, L2Q. And entropy is dimensionless. So the entropy has to be proportional to the volume times TQ. So it's volume times TQ. That's the answer. And there's some coefficient in front, which we cannot figure out. So similarly, the energy in this box is the 7 Boltzmann law that was mentioned earlier when we talked about that one distribution. Then, given this, you can then go on to black hole entropy and temperature, which I won't talk about in this lecture because there's not enough time. But I still have 2 more lectures in Haida, so some of these I would go into details on some of this. Okay, so when I was a student, I always thought to think about what is a great piece of physics that I learned. Well, one of the greatest pieces of physics, in my opinion, is Van der Waals law. Van der Waals is a great pioneer of fly-by-night physics. He replaced Boyle's law. Boyle's law was PV equals NT. You have an ideal gas, the pressure and volume, number of molecules times time. And students in textbooks now take Van der Waals for granted. But not the great people recognize the great people. Maxwell recognized Van der Waals' greatness. And in fact, I read that it was interesting. He even decided to learn Dutch in order to read Van der Waals' paper, the original. And then he, in fact, of course, the time standard is very useful, being Maxwell. He ended up making an important contribution. So you probably know this is Maxwell's construction for phase transition. So what Van der Waals did, nowadays you would write down some Holzworth equation or some proper equation or God knows what, and or some people just turn on a computer. But Van der Waals asked himself, how do I modify Boyle's? And what he said was that the molecules have volume, right? They have size. And so suppose each molecule has volume V. Then we don't really have the full volume of the box to roam around. We should subtract from the volume the number of molecules times V. And then also the molecules have repulsion and attraction between them. And so the attraction should go like the density squared with some unknown coefficient. And so that was what he wrote down. He introduced 2 fundamental constants, 2 constants, not fundamental. So the thing that I want to emphasize is that what Van der Waals did was not merely some dumb garden variety fit to data. You know, I go down, I'm at some institute for theoretical physics, which means that every day there's 3 or 4 talks. And I sit at my desk and I ask myself, should I go downstairs to listen to one of these talks? So now I go down less and less and less and less. And eventually I think I'm now going down to listen to 1 talk a month and 1 talk every 6 months and so on. So, and many of the talks are just some dumb garden variety fit to data. So textbooks tend to minimize Van der Waals' contribution. And so they are guilty of the bias of hindsight. Remember, when Van der Waals proposed this equation in 1873, most physicists did not accept the reality of molecules. They don't even accept molecules. So it's really important to realize 2 is not just some 2-parameter fit, but the 2 parameters actually tell us about the size of the molecules and the attraction between them. And furthermore, it indicates to experimentalists the range of experiment and pressure at which helium, for example, could be liquefied. That's very important. So the impact, Van der Waals' work has huge impact, not just on theoretical physics, but on experimental physics and on technology. Okay. And in fact, it's not a surprise that the Dutch were the first to be able to explore low temperature physics, to liquefy helium, and then discover amazing phenomena like superfluidity and superconductivity. Okay. So Van der Waals is an extremely important figure. Now, after Van der Waals, of course, Van der Waals talked about interaction between molecules. But let's now talk about ideal quantum gases. So ideal means no interaction. but the quantum statistics are crucial. So then the crucial parameter is the ratio of the de Broglie wavelength to the particle separation. So this is the crucial parameter. You recognize that this is the de Broglie wavelength for particles moving with energy T. And this is the interparticle separation. So the ratio of these two is what controls the quantum contribution. So you can see from this is either high, you can think of this as either a high temperature expansion or low temperature expansion. Okay. And from this, just doing some fly-by-night guesswork and dimensional analysis, you can deduce a lot. Okay. But I look at the clock and I see that it's already 12:30, past 12:30, but of course I took a bathroom break, so maybe I should give you back that time. But fortunately, I have 2 more lectures in Taida, so I could go into some of these details, and I could also talk about other areas of physics, such as gravitational wave emission from black holes and perhaps some particle physics and so on and so forth. So I will end and skip over these few slides. I have a few more slides, and you can see all this. Now, I'm going to go over some of this on the blackboard. The interesting thing is in 2 weeks, I'm going to Beijing to give the same lectures. And my book is being translated into Chinese in China, in Dalu. And it was very interesting because my wife, by the way, I put my wife in charge of all my books in Taiwan and China. So she was negotiating with the publisher and the translator on how to translate fly-by-night physics. So it turns out, amazingly enough, 300 years ago in China, there was a book published, almost fly-by-night physics, but of course not physics, but it's called, in 300 years ago, this guy from the town, he wrote a book called Ship Moving in the Night. Okay. This book, in fact, in China, it was published in the new edition. Okay, so why does this guy wanted to write this? So this is sail by night boat. Okay, sail by night, not physics, and it's a lot of ships go in the night because already a long time ago in Song Dynasty and so on, there was such things, and so for the longer distance, you need to go at night. Well, I understand this very well. Every time I come to Taiwan, you have to fly at night. So to get to your destination in the morning. And so this was very familiar to the Chinese, to the ancient Chinese. And this guy said, 天下学问, all the knowledge in the world, it is the night sailed ship that's the most difficult. And why is that? It's because the people from Zhejiang province, they like to read books. So I guess I'm originally from Shanghai, so maybe that explains why. I'm interested in reading books. And then on these night ships, so he said that because people read so many books, that all these young guys, so this is 后生小子. So I think the 后生小子 is all the people in the room except for Gao Yongzhen. And a few other people. And all the 后生小子, they all read. And even if they don't have any achievement when they're 20 and become a craftsman, so every walk of life, they know a lot of books. So on these night ships, everybody asks him questions. So on the long night, I guess people don't go to sleep. But on my flight to Taiwan, on Huaha, the airline, mostly nobody asked me any questions. And so he said that with these night ships, that's why he needed to write this book, because he said that all these little guys, they know a lot of stuff. And so that's I conclude my talk with this book. So this is being translated in China. Okay, thank you very much. So on Tuesday, Thursday, I will give the continuation of this lecture, but it will be on the blackboard. And it will be in more detail and go at a slower pace. Now, you also know that it's absolutely impossible to cover this book, because this book is a course at the University of California. So it's for a whole quarter. And now the chair wants to make it into a regular course. I hope that, I already taught it like 7 or 8 times, so I hope that I could hand it off to somebody else. But thank you very much. So he's the TA.
Yeah,
So if you have any question, you could ask him.
There will be 2 more courses, one on this week and the other on the next week.
And you're supposed to write notes or not write notes? It's
Well,
up to you.
Okay.
Okay. So 你们去找他。
So I put it in my pocket. I'm not done with see that. Great job. What's the Nelson? What?